Well, the weather was certainly nicer last week, wasn't it? Today we're going to do Chapter 11. It's radioactivity. This is an aerial shot of the nuclear power plant in Japan, Fukushima. They had an earthquake and a meltdown and a tsunami and whatever else. Obviously a very bad accident. But what I wanted to point out in this picture, there's a plant right here. And you see all those little homes all around it? You know, gee, I'm sure glad I didn't live there. But, I mean, they're very, very close. Real estate, I guess, is treasured in Japan. Big clouds of radioactivity coming up.
They had to be in quarantine, right? The people, all the surrounding people living
Yeah,
there.
well, they left as quickly as they could.
Right.
And they haven't been able to come back. But a lot of these homes had little gardens where they grow produce and stuff like that. And after the fire settled down, and a little while, a few months later, people came and explored in the area. And a couple things that are cute that they found. Carrots, 2 for 1, or corn, I mean. And these are tomatoes. Yeah, there's definitely some genetic mutations going on there. But my favorite, of course, is the white shark seagull mutation.
No way, that's real?
No, it's not.
I was going to say, no, I can't.
It's Photoshop, but it's fun anyway. Anyway, these are real. Yeah.
That looks more realistic. I'm like, oh.
So, today in Chapter 11, we're going to talk about review isotopes and then talk about the concept of radioactivity. We're going to do alpha particle emission and nuclear equations, beta particle emissions, radioactive decay and what a half-life means, positron emission. Positron is interesting, it's antimatter, and how that's used in a PET scan. Finally, nuclear fission, where we'll talk about bombs, how to make one. And finally, fusion. Any questions before we get started? All right, let's just review a little bit here. We'll be using atomic symbols a lot in this chapter, so let's just review it. Remember, the atomic number of an element gives the number of protons that are in the nucleus. That's what defines what an element is. Doesn't matter how many neutrons, how many electrons. If it has 6 protons, it's a carbon. We show this using an atomic symbol. We put a mass number and the atomic, or in the number of protons in our atomic symbol. We start off with the symbol for the element. The mass number is a superscript in front, and the atomic number, number of protons, a subscript in front. We talked about isotopes way back in chapter 2, I think. Again, since anything with 6 protons is going to be a carbon, but it doesn't matter how many neutrons you have. You can have carbons with different numbers of neutrons that changes the mass number. Carbon exists largely as carbon-12, a little bit of carbon-13, and a tiny trace of carbon-14. We'll talk about how carbon-14 comes to be a little bit later today. Any questions? Well, the phenomena of radioactivity was discovered by accident. A French chemist working on phosphorescence in a dark room. Someone accidentally placed a bottle of a uranium salt on their stack of photographic plates. Now that was a big deal at the time because you had to make these things by hand. And when they went and they developed them, they saw these big smudges everywhere. Couldn't quite figure out where they came from, but I'm sure somebody got in lots of trouble. The source of this was later discovered by Curie and others, and what they found was that the uranium salts were emitting particles, and they called that radioactive, and that these particles consisted of three distinct types: alpha particles, beta particles, and gamma rays. Beta particle is just an electron. Now, this is not coming from the electron cloud. This is coming out of the nucleus. What's an electron doing in the nucleus? We'll figure that out in a bit. Alpha particle, 2 protons, 2 neutrons. Basically a helium nucleus. This has a charge of +2, this is -1. The most energetic of the rays they found was called a gamma ray. It had no mass, no charge. Basically, it's a photon, a ray of light with lots and lots and lots of energy. And the energy is shown on this little diagram. Alpha particles basically are heavy, they're slow in general, and they're weak. Piece of paper totally stops it. Beta particle, much more energetic. This is supposed to represent a centimeter of lead, and that's typically what you need to stop beta particles. Gamma rays, much more intense. This represents 10 centimeters of lead. That will stop some of them. Many of them just travel straight through. So gamma rays can be very, very intense. We detect radioactivity, typically, using something called a Geiger counter. This is a Geiger counter from the 50s, actually, civil defense. And this is the probe. What you do is take the probe off, walk around like this to see if there were radioactive waste or whatever around you. The way this thing works, something like this. The probe is basically an evacuated tube with a cathode on the outside and anode on the inside. Partial vacuum here. There's a gas in here, usually something like argon, but it's at a very, very low pressure. You have a power supply, puts a voltage between here and here. If a radioactive particle, called ionizing radiation, just happens to come through, it like sets a little bolt of lightning off inside here. It flashes between the anode and the cathode. The electronics pick it up as a click. So you hold this next to something radioactive, and you hear that. Each one of those is a radioactive particle entering the probe. All right, let's talk about our particles one at a time here. We'll start with alpha. Alpha is the heaviest, the slowest, but the most toxic. Consists of 2 protons, 2 neutrons. This is a helium nucleus. Helium atom with no electrons. If we start off with a nucleus that looked like this, 12 protons, 12 neutrons, and this lost an alpha particle, what would happen is, here's our alpha coming off. We're now down to 10 protons and 10 neutrons. The mass number will drop by 4, because we've lost 4 things from our nucleus. And the atomic number will decrease by 2, because 2 of those things are protons. All right. An isotope that spontaneously emits an alpha particle is uranium-238. Now, uranium-238 will lose its helium nucleus, that is mass number 4, 2 protons, no electrons. This is the alpha particle. Now, what's left is going to have 2 fewer protons in the nucleus, so it's going to be a 90 instead of a 92. Let's look at our periodic table here. Somewhere. There it comes. We're starting here at uranium. We're losing 2 protons, so we're down here at thorium. The mass number, we started at 234, we lost 4, 238, we lost 4, we are at 234. This is what's called a nuclear equation. Sometimes the helium nucleus is shown by the symbol alpha, same thing. Nuclear equation, just like any other chemical equation, has to be balanced. But here we're balancing in terms of number of protons and total number of protons plus neutrons. Mass number, 234 plus 4 is 238. 90 plus 2 is 92. They must balance in a balanced nuclear equation. Any questions? Well, let's do one. My battery must be getting weak. Thorium-230 loses an alpha particle. Write the nuclear equation and show what element is formed. Now, in the previous example, I just want to point out, we started off with uranium, and we made a new element, didn't we? We made thorium. So here's thorium losing an alpha particle. Thorium, down here, 90 protons, mass of 230. This is going to lose our alpha particle. Our mass number is going to change from 230, we're going to lose 4. The atomic number is going to go from 90, going to lose 2, going to make 88. If we look at our periodic table, we're starting with thorium, 88. Oh, radium. We have converted thorium to radium. The mass number started at 230, we lost 4, we're at 226. Any questions? Well, let's do it again. Polonium-214 loses an alpha particle. Write the equation. So let's find polonium. It should be right there. 214 is the mass number. We will lose the alpha particle. Go ahead and fill in the missing element here. We're starting at 84 and losing 2. Well, if we lose 2 protons, we're not at 84, we're down here at 82, and that's lead. Our mass number started at 214, we lose 4, we're at 210. Any question? Fairly simple. We take a nucleus, lose 2 protons, 2 neutrons, make a new element, different mass number, different atomic number. All right, let's talk about beta particles. You know, a neutron is neutral. A proton is positive. Electron is negative. Neutrons live in the nucleus, so do protons. It's tempting to think that if you take a proton and an electron, put them together, plus and minus, you get a neutral, right? The masses kind of work. Well, that's not exactly how it is, but by George, it's close enough. If a neutron living in the nucleus decides it's tired of being a neutron, it can shed an electron and become a proton. Kind of an interesting thought. So here's our nucleus. Again, we're 12 and 12. What's going to happen is one of these neutrons is going to decide it doesn't want to be a neutron anymore. It'll lose lose an electron and convert itself into a proton. There goes the electron. It is now a proton. Now we have 13 protons and 11 neutrons. The mass number, however, has stayed the same. We started off with 12 and 12. We have 13 and 11. But we have 1 extra proton, so the atomic number increases by 1. All right, thorium-234. 90 protons. One of these will spontaneously emit a beta particle. When it does, the proton comes from a neutron, so the mass number will stay the same, but the atomic number will increase by 1. So instead of 90, we're at 91. So we started here at 90. We gain 1 more proton. We're at praseodymium, P8. The mass number, however, does not change because the extra proton came from a neutron. So let's show our particle here. Our mass number hasn't changed, so the mass number of our particle we lost must be a 0. We'll use beta for the beta particle. But what do we show for an atomic number? Remember, these 2 must add up to that. These 2 must add up to that. That means the beta particle must be shown as a -1. Atomic number of -1. That's simply to make this balance. Any questions? All right, bismuth-210. It'll lose a beta particle. Let's write the equation. We're going to lose a beta. It'll look like that. The mass number isn't going to change, is it? But we are changing 1 neutron into a proton, so this is going to go from 83, which is here, to 84. 84, let's see, right here, polonium, PO. And again, our mass number will be 210. So with an alpha particle, we moved this away 2 spaces. With a beta particle, we moved to the right 1 space. Now, polonium-210 turns out to be an alpha emitter. When this thing loses its alpha particle, we're going to go from 84, going to lose 2, we'll be down at 82. So we're starting here, going to go down to 82, that's lead.
Yeah, alpha particle.
And the alpha particle. We're starting at 210, we're going to lose 4, lead 206. Now this alpha particle that polonium spits out turns out to be exceptionally energetic. Remember I said you could stop it with a piece of paper? Well, not if it's polonium-210. Turns out this is one of the strongest, most energetic alpha particles there is. It's also a favorite poison of the KGB. A few years ago, there was a dissident Russian that was poisoned with a microgram of polonium-210. The KGB invited him to lunch, gave him a cup of tea, died 2 weeks later. Really bad stuff. Any questions? We'll talk about the energetics of this when we do half-lives. All right. Radioactivity isn't just for the heavy elements. Neon-19 loses a beta particle. Go ahead and write the equation. Remember the beta particle, 0 mass number, -1 atomic number. So we're starting here at neon. We have converted a neutron into a proton. So we're going to go here, down 1 row. We're going to hit 11, and that's sodium. The mass number doesn't change. We just made sodium 19. Any questions? Now, gamma particles really aren't particles from the nucleus at all. The nucleus just simply sheds excess energy. Quite often when a nucleus loses an alpha particle or a beta, it's left in a, quote, unsettled state. So it's all excited. It loses its excitement in terms of a gamma particle. The more excited it is, the more energetic this guy is. You can take a Geiger counter right here in this room, turn it on, and you can hear clicks. Those are gamma particles coming from way out in outer space. Very, very energetic, can travel forever. Kind of like a super X-ray or a ray of light. Again, they're very highly energetic, and they're ionizing radiation. So let's just do a little list here. Let's go ahead and fill in the products for these nuclear equations. Radium is going to lose an alpha particle. Our number of protons is going to change from 88 to 86. So we're starting here at radium here. Going to lose 2. We're at 86 radon. The mass number decreases by 4, giving us 222. Chlorine, relatively light element, loses a beta particle. The atomic number will increase by 1, but the mass number will not change. So we're at 17. We will increase by 1. That gives us argon. Argon is 18 protons in the nucleus. Argon 39. Lead 214 loses the beta. It's going to gain 1 atomic number. So from 82, we will go up to 83. We're starting here with lead. 83 is going to take us to bismuth. The mass number will not change. We have bismuth 214. And finally, radon is going to lose an alpha particle. It's going to drop from 86 down to 84. That gives us polonium. Mass number will decrease by 4, giving us polonium 218. Any questions?
Yeah, can you explain how you got on polonium again? Like at the video? Like, did you set stuff from helium and polonium?
This last one?
Yeah, the last one.
Okay, well, we started off here with radon. So we're here. We are going to lose 2 protons, so the atomic number drops from 86 down to 84.
Oh, okay.
That's polonium. This will drop from 222 by 4, polonium 218.
And you're always going to subtract them across the cross, right?
These must add up. These must add up.
Thank you.
All right, this is the last tutorial for the class. Nuclear equations. It's simple, actually. You're starting off with an element. These are in a slightly non-standard format because that's just the way they are. But magnesium 26 is going to lose an alpha particle. Okay? That means that the atomic number will change from 12, we'll lose 2, we're going to be down at 10. There we go. The mass number will drop by 4 to give us 22. We have to look at our periodic table, so you can print one of these if you want. Let's see, we're looking for 10. Oh, there it is. Neon. Neon 22. Nice simple tutorial just to review how to write balanced nuclear equations. Blackboard, pretty much the same thing. Any questions? Well, let's think a little bit about nuclear decay. Remember, in nuclear decay, you start off with one element, you lose something, and you change to a different element. So let's just follow the course of uranium as it does its decomposition. On this little chart, alpha decay is shown this way. We drop 1, 2, 3, 4. So we're here. This is atomic mass units here. So we use 4 for our mass number, and we're down 2 from our atomic number. So uranium is here. It will lose an alpha, drop down to give thorium 234. That loses a beta to get prolactinium 234. Then uranium 234. Another alpha down to thorium. Another alpha, we're at radium. And another alpha, we're at radon. Now you may have heard of radon, especially if you live in a house or you buy a house or try to sell a house. Uranium is a very rare element. It occurs in rock, very low concentration, and it's worth a lot of money. So what you do is you take rock and you grind it up and you extract what's left, the powder, extract it with acid and whatever, and you can get the uranium out. But when you do that, you're left with a mountain of ground up rock, right? What do you do with that? Well, obviously, you use it to make cinder blocks or cement or whatever, because it's just ground up rock, right? But this ground up rock in our cinder block still has some uranium-238 in it. Now, if you happen to build a school or a basement with cinder blocks or cement, that means that the walls are going to be seeping out radon-222, which is a gas, and it's toxic. So, if you have a basement sealed up nicely so it doesn't leak, it accumulates radon. So before you can sell a house in Illinois, somebody has to come in and check your basement for radon levels. If you're full of radon, you stop breathing when you're in the basement, you have to put in a fan to exhaust it and get fresh air in there. When I was at UIC, the entire building was made of uncoated cinder block. And I could actually sit in my office with an alpha detector, put it up next to the wall, and detect alpha particles coming out. Yeah, amazing. Any questions? All right, well, the time that's required for an unstable nucleus to decay by 50% is called a half-life. Now, what that means is you have some radioactive element. We'll start off here at time 0 at 100% of this element. It will sit there and change into something else. As it does, its concentration will drop. When it drops down to half of what it used to, this is called the half-life. An example, strontium-90 loses a beta particle to give yttrium-90. The half-life for this is about almost 30 years. Now, for people of my generation, This is a very important sort of decay because strontium is right here underneath calcium. They're essentially the same size, and anywhere in a chemical structure that calcium will fit, strontium will fit too. All right. In the 50s, everybody figured out how to make atomic bombs. And we blew them up in Nevada. The Russians blew them up in the Siberia. France and England blew them up who knows where. Not there, but one of the colonies. And all of this radioactive dust was souped up into the stratosphere, circled the Earth. And every time it rained, we would get what they called fallout. Fallout, radioactive particles raining down. One of the things that's formed when a bomb goes off is strontium-90. So somebody asked, gee, I wonder if this might be fitting into calcium spots in the body. So they did this experiment. Hundreds of thousands of baby teeth from kids of that generation. That's me. 50 times more strontium-90 than kids born later. Now the good news is the half-life is 30 years, and this was roughly 60 years ago, right? So most of it's gone, or at least 2/3 of it gone. We're down here somewhere. But yeah, what happened is that it would rain, and it would rain in Wisconsin. The radioactive fallout would come down, water the grass, it would grow. Cows would eat the grass. Then they'd milk the cows. Milk, strong bones, healthy body, and strontium-90 at the same time. So yeah, we poisoned a generation here. Half-lives vary a lot. This is a long scale. 10 to the 22nd, that's billions of years, going way, way down to very, very small numbers. Typically, particles down in the lower half of the plot here are much more energetic than the particles from the top half. Just an example of some half-lives. Uranium-238, 10 to the 9th years. It's an alpha particle emitter, long half-life, low energy. Uranium-235, the stuff that bombs are made of, 10 to the 8th. Thorium wins at 10 to the 10th years. Plutonium. Plutonium-239 is used to make bombs. Okay? We have a lot of plutonium in the world right now. We have roughly 550 tons of plutonium. Now, it's a moderate half-life. It's energetic. We have, like I said, 550 tons, right? If you take 600 grams, that's enough to poison every living thing on Earth. And we have 550 tons of it. Yeah. Carbon-14, we'll talk about that. Strontium-90, we did that. Polonium, remember I said this was a deadly alpha particle, short half-life. Iodine, 131, very short half-life, about 8 days. This one is important because in Japan, when the nuclear power plant burned, and in 3 Mile Island in Pennsylvania, when that had a meltdown. One of the things that is released are huge clouds of iodine-131. Iodine-131, 3 Mile Island, big cloud of the stuff. The real danger is that we absorb iodide from the environment to make thyroid hormone. So if you just happen to be in 3 Mile Island at the time, what would happen is you would breathe, hopefully, and when you did, you would inhale iodine-131. It would accumulate in your thyroid, and you would get cancer. Very energetic particle. However, there's a very simple fix. As soon as this plant started to melt down, they ran around giving everybody potassium iodide pills. And you take these, your body is now saturated with iodide, you don't absorb anymore. Do this for 3 or 4 half-lives, and you're good. Any questions? All right. A problem. Cobalt-60, half-life is 5.3 years. How much of a 1 milligram sample is remaining after 15.9 years? How do you calculate that? Well, of course there's an equation. I am not going to ask you to use this equation to remember it. I would be standing here for the rest of the day trying to tell you how to type it into your calculator. You don't want to do that. So instead, the questions that I ask about half-lives will be obvious. For example, if the half-life here is 5.3 and we're at 15.9, we start with 1 milligram. After 1 year, we've lost half of it. We're at half a milligram. The second year, 2 half-lives, we lose another. 3 half-lives, 0.13. And finally, after 10 half-lives, we would have over 1. This is, again, there's a story for everything. When I came here to Triton, and I was teaching a course where we talked about radioactivity, I thought, gee, it'd be neat. Take a Geiger counter and a sample of something. So I rummaged in the cabinet, and I found a sample of cobalt-60. Well, cobalt-60 is not something you keep in a cabinet. It's something you keep shielded behind 10 centimeters of lead. Okay, it's a bad one. And I thought, oh my goodness, what's this doing here? And then I looked at the date. They bought it when the school opened in '64. So I did a quick calculation. We are over 10 half-lives, and it's dead. That's a good thing. All right. Carbon-14. Where does that come from and who cares? Well, carbon-14 comes about from a very interesting phenomenon. In the upper atmosphere, we have nitrogen. Nitrogen-14, that's just plain regular nitrogen. We also have a sun up there somewhere, and the sun spews neutrons at us constantly. That's what makes the northern lights. Okay. Well, if a neutron just happens to run into a nitrogen-14, it can stick. It hits the nucleus and it sticks. That makes nitrogen 15. But nitrogen 15 is very, very unstable. Very unstable. And as soon as it forms, it breaks down. It spits out. See, it was unstable. Spits out a proton, and that leaves carbon 14 behind. So constantly in the upper atmosphere, carbon 14 is being produced. It's converted to carbon dioxide eventually. Now, the half-life is 5,700 years. Converts back to nitrogen 14. Let's pretend that we happen to be alive. If you're alive, you're breathing, right? You're inhaling carbon dioxide. And a small amount of that has C14 in it. That means in a living thing, there's a ratio between C14 and C12. Now, if you stop living, for whatever reason, you stop breathing, what happens is you still have the C14 you started with when you were alive, but every 5,700 years, half of it decays. So you can take a sample of something that's dead, look at the C12-C14 ratio, the half-life, and you can tell when it died. That's kind of neat. It's radioactive dating. This was tried on the Shroud of Turin, but they wouldn't let them have a piece of the real cloth, so it didn't work. But this is the way it's supposed to work. Pretend you're a saber-toothed tiger. When you die, your C14-C12 ratio is something. It's a number. After 5,700 years, you've lost half of it. Another 5,700 years, you lose another half, and another half, and another half. So you can dig up something like this, measure the C12-C14 ratio, and know when that thing stopped living. It's kind of neat.
Based off carbon 14.
Yep, carbon 14 dating. All right. Well, I commented that the notion of a neutron shedding an electron and becoming a proton was kind of strange. This is even stranger. If a proton decides it's tired of being a proton, it can shed its positive charge and become a neutron. Okay. This positive charge is called a positron. What it is, it's a positive electron. A positive electron. That makes it antimatter. Antimatter is real. Not just on Star Trek, but Scotty would run around and say, you can't let the matter and antimatter mix. It's real. Here's our atom. What we're going to do is take a proton, break it down, form a positron, convert the proton to a neutron. It comes out as a positive electron. The mass number will stay the same. The atomic number will decrease by 1. That's because this guy used to be a proton, now it's a neutron. proton loses a positron and becomes a neutron. And an isotope that does this is carbon-11. It loses its positron, becomes boron-11. The mass number does not change. We show a +1 here to balance this out. 1 plus 5 is 6. Strange stuff. Well, not only that, but because this is really antimatter, in fact, if it does encounter matter, so a positive electron and a negative electron, if they collide, you get total annihilation, just like Scotty said. These annihilate each other and you form two high-energy gamma rays. But the neat thing is that these gamma rays are produced in opposite directions, exactly opposite directions. So this phenomenon has been adapted into what we refer to as positron emission tomography, a PET scan. Here's a PET scan. This is a ring of basically Geiger counter tubes surrounding your patient, and we're pretending that this poor guy has a tumor right in the middle of his head. The tracer we use is fluorine 18. Loses positron to give oxygen 18. As soon as the positron is produced, you put it in with glucose, labeled deoxyglucose with fluorine 18 right here. This is now our carrier. When this decay happens, you run into an electron and you get two gamma rays. All right? So, here's our tumor. This looks like glucose. Tumors and your brain, actually, don't do oxidative metabolism. They only do glycolysis. So when you eat sugar, tumors will suck it up. So this concentrates in the tumor. So right now, it's in the middle of his head. When decay happens and we get gamma rays, they go out in opposite directions. My computer says, oop, I got one. Yep, right along there. Then it happens again. And there it is. And again. And your computer processes all of these decays and comes up with an image that shows your tumor as a spot. Kind of neat, really. This is a real PET scan. Somebody with very bad GI cancer. And yep, all those little spots there, that's concentrated tumor. Very, very important, widely used diagnostic technique now. Any questions? Well, let's do a couple simple positron equations. Arsenic, 70, will lose a positron. That means the atomic number will drop by 1. And the mass number will stay the same. So here we are with arsenic. The atomic number drops by 1. That gives us germanium. It will be germanium 70, and that's it. 32 plus 1 is 33. 70 plus 0 is 70. Another one. Not supposed to show yet. Krypton 77. Here's a positron. Number of protons will decrease by 1. So we're here at krypton. We lose, and we form bromine. Bromine will have a mass number of 77, and it will look like that. With these, I ask you to give me the element that's doing the decomposition. So we just work backwards. The mass number is going to be the same over here, 79. Our atomic number is going to be 36. 35 plus 1. So 35 plus 1 is 36. We're at krypton. Krypton 79. Yep. Iron. Going to change from iron. 1 heavier. Going to go to 27. So we're starting off here with iron. 27 is next door. That's cobalt. The mass number will be 58. And that's our nuclei. Any questions? Let's just mix them up a little bit. Typically, oh, you want to go back?
It was just one last one, right?
Okay, hurry on.
Alright, there you go. Thank you.
All right. Typically, on exam 2, I will give you a nuclear equation to fiddle with. Either go forward or back or something. Figure out what particle, whatever. So, chlorine 39, beta particle. We're going to go from 17 to what? 18, because that's a minus 1. We're starting here at chlorine. Go to 18, we're at argon, 39. Neon, beta particle. Going to go from 10 to 11. Neon is here, 10. 11 is sodium, 19. Nobelium, big heavy guy, is going to lose something to give fermium 253. So what are we missing here? Our mass number has dropped by 4. Our atomic number has dropped by 2. That screams at you, I am an alpha particle. The element is fermium. We're here. And we've lost an alpha. Finally, plutonium-239. This is the stuff that's in bombs. Loses an alpha particle. This is the one we have 5.5 tons or whatever. No, 50 something. We have a lot of this stuff. Anyway, if it loses its alpha, we're going to drop 4 mass units. We're going to drop 2 atomic numbers. So we are here somewhere. Where's plutonium? Oh, there it is. We are going to drop from 94 down to 92. That makes it uranium 235. Both of these are used in bomb making.
Yes.
This next plot here shows The stability. This is a one-to-one line for neutrons and protons. Most things have too many neutrons relative to the number of protons, especially as you get up in the heavy elements. If you have excess neutrons, you tend to have a beta emitter, excess protons an alpha or particle positron. This little black line is referred to as the line of stability. Difficult line to walk, but these long little black lines are pretty much stable. All right, let's get into the fun stuff. We talked about nitrogen. Neutron from the sun comes flying in, hits the nucleus, and it sticks. This causes the nucleus to become unstable. When it does, it breaks apart and gives us carbon-14. This is called transmutation. Where you stick a particle in, get something unstable, it breaks apart. This is the thing that gives us the atomic bomb. $235 can absorb a proton easily. Big nucleus comes in and it sticks. That would give us uranium-236, which is a very unstable nucleus. Here is uranium-235. Let's just pretend you have an atom of it sitting around, and a neutron comes careening in and hits the nucleus. This is what happens. Here's our uranium. Here comes our neutron. It sticks. As soon as it forms, it breaks apart. Now, in this particular fission, what happens is we form two heavy nuclei and we release 3 neutrons. These are high energy neutrons. We get krypton, we get barium, and we get neutrons. This also releases a lot of energy when you take and break this nucleus apart. Each fission event, about 200 million electron volts in energy. That's more than 2 trillion degrees Kelvin on an atomic scale. Lots and lots of energy. Well, we have released these 3 neutrons, haven't we? If these 3 neutrons just happen to run into another 3 uranium-235s, what happens? They split too. This is called a nuclear chain reaction. You hit it once, get 3 more, those 3 go, you get 9. Those go, you get 27 high energy neutrons, etc., etc. With this huge energy at every split. This is classically shown using mousetraps and ping pong balls. That is a nuclear chain reaction. What we're going to do is drop this down in this little cage filled with mousetraps and ping pong balls. Here they go. Whoosh. That's a chain reaction. So one more time, but basically this is nuclear fission. We take uranium-235 plus a neutron, we get unstable 236, and it splits apart, giving us 3 more neutrons that continue the chain. Now this is size dependent. Size does matter here. Because if you don't have enough uranium-235, these just kind of get away, don't they? This is called a critical mass. If you have a little bit of uranium-235, what happens is these neutrons escape. Now this gets warm, yeah, but it doesn't explode. However, if you have what's called a critical mass, this is just enough so that almost none of the neutrons get away. This heats up very rapidly, typically within a few microseconds, and can explode. This is a demonstration of a critical mass. Again, we're talking ping pong balls. There again, lots of stuff. As soon as you set it off, it just goes like that. Critical mass, ping pong balls don't escape. However, if you have low density stuff, or not much of it, you can take a ping pong ball and bounce it right down the middle. Now you have to wonder how many times they had to do that without accidentally setting off at least one trap. But nonetheless, it can be done. This is a non-critical mass. The other represents a critical mass. In a nuclear power reactor, since neutrons are the bad guys here, you have what are called control rods. Control rods absorb neutrons. So you have your pellets, your radioactive stuff in here. You move these rods down if you want to absorb the neutrons. If you want the reaction to go faster, you pull them out. It works, but you'll see that this can be a very dangerous thing. Any questions? Well, if you're in a nuclear reactor, you want to control all this, right? But if you're using this technology to make a bomb, you don't want any controls at all, do you? This is a remarkable little film clip from the 50s. This is a howitzer. Barrel's about 4 inches diameter. What they're doing here is they're shoving in an atomic bomb. And they're also happy to throw it. And it shoots downrange 3 miles. And it lands. And there it goes. Now the first thing that happens, they have stuff all around the site, old buses. That's the shock wave. Next comes the blast wave. Here it comes. Then it starts sucking all this dust back up. Sucks it up into various mushroom cloud, which is now highly radioactive. Goes up in the stratosphere, rains down on Wisconsin. These guys were sitting there a couple miles away, just filming away. They're probably dead by now. But yeah, this bomb here all of that nonsense had a yield of about 1 kiloton. One. First time we dropped on Japan was 13 kilotons. Today, they typically run 100 to 200 kilotons. 1 kiloton is considered a dud. Yeah.
Did that create plutonium too as well?
Plutonium bombs, slightly different.
Okay.
These are the guys that designed it. You can tell it's authentic. See the chrome over? Pocket protector. But they're so proud of it. It's this little tiny thing. 1,000 tons of TNT. Well, how does this work? This one doesn't work this way, but the first one worked like this. Called a gun-type fission bomb. What you do is you have essentially a long barrel, lots of shielding around it. It's a gun barrel. And you have taken your critical mass and split it into two parts. This one is hollow. This is the plug that fits in the middle. You set off the conventional explosive at one end. That takes the ring, pushes it down the barrel, and it assembles into a critical mass. About a microsecond later, this happens. This is actually the first real bomb we devised and set off, about 10 kilograms. Again, this was in the body. I say don't try this at home because it's simple enough that if you had uranium-235, you could. All you have to do is take two non-critical pieces, get them together, hold them there for a microsecond, and it works. That's it. That's why we get so upset when low stakes are making uranium-235 because it is so simple to make a bomb. So simple. But nobody makes bombs like that anymore. Takes way too much stuff. Instead, they came up with a better way called an implosion bomb. Here, we use 239 plutonium, have a little ball in the middle that's subcritical. So it's just going to sit there. We surround it with explosive charges. The idea is you set the charges off, it will compress the plutonium in the middle, density will go up, it will hit critical mass, and explode. Something like this. Here's our explosives, there's our plutonium. We set them off, compress the plutonium, hits critical mass, and there it goes. The problem with this is the timing. All of these guys must go off at exactly the same instant. Exactly. That's why it is so difficult to make an implosion bomb. The shell looks like a soccer ball. These are all the explosive pieces, and it's about the same size as a soccer ball. That's the plutonium sphere. All you do is you put this guy inside that guy, and you've got a bomb. But the timing must be exact. Literally the size of a soccer ball. Now, you know, this has led to a major, well, I would say a trick, but the Russians do it, the Israelis do it, we do it, everybody does it. This is not considered a bomb. We have a treaty with Russia that we can only have 2,000 or 3,000 bombs. So can they. But it says nothing about how many plutonium pits you can have or how many explosive spheres you can have. So if you decide one day you want to make a bomb, you simply pick it up, put it in there, wire it up, and you've got a bomb. We have roughly 25,000 plutonium pits sitting on shelves next to 25,000 empty casings. Yeah. Just pick it up, put it in, and it's good to go. Now, because this is a soccer ball, literally, you can make them very small. This is an army backpack. It's big because it has shielding, but the idea is some GI puts this on, carries it across enemy lines, drops it on the ground, and runs like hell, and it goes off. You can make implosion bombs very small, just like the one we saw at the start. The little howitzer shell was implosion. This is a suitcase bomb. Yeah, you can make it small enough to fit inside a suitcase. This is a Russian suitcase bomb, actually. When the Soviet Union fell apart, the guards weren't getting paid, and so they walked away. And a whole bunch of these guys went missing. We admit to losing about 11, but there are probably 50 to 100 out on the black market somewhere. All right, well, fission bombs are bad things. They're easy to make, especially if you have lots of 235 around, but they're little. Okay, it's tough to make one that's more than 100 kilotons. Fusion bombs, on the other hand, are much bigger. If you take deuterium and tritium, subject these to a great deal of physical pressure and temperature, you can squeeze these two nuclei together, spit out a neutron and a helium nucleus, and get 3.5 million electron volts as you do it. That's a lot of energy. This is fusion. That's what runs the sun. Except the sun is big enough it doesn't need to use deuterium and tritium, it just uses hydrogen. Squeezes them together, makes isotopes, squeezes those together, eventually makes helium. Energy released at every fusion. Well, of course somebody realized this and designed a bomb. This is a hydrogen bomb. Down in here we have deuterium and tritium. What is this up here? Looks familiar, it should. That's an atomic bomb. You use an atomic bomb as a detonator to set off the hydrogen bomb. That's the detonator, the plastic cap. 52, we made our first one. Took a very nice little island in the Pacific, rendered it uninhabitable forever. And we continued to build and explode these things, so did the Russians. The Russians got a hold of the plans, and they were very good at designing these bombs. The biggest one that they made was actually a 50 megaton device. Now it was supposed to be 100, but they dialed down the yield because they calculated that there was no way you could drop the thing and get far enough away without being vaporized. So this is Siberia. This is the most impressive explosion you'll ever see. They're 50 miles away. This mushroom cloud extends all the way up into the stratosphere. Miles up, and you're 50 miles away from it. It's an impressive looking cloud. Well, you might ask yourself, why in the world would the Russians want to make a 50 megaton device? You know, you could do it with 13 kilotons, okay? Why 50 million tons? Turns out that the Russians were damn good at making bombs, but their missiles, the guidance system was really bad. So you shoot it in the air, you had no idea what was going to land. So if you make the bomb big enough, it doesn't matter, does it? So this was the Cold War. They were making bombs, we were making bombs. This is Lakeshore Drive. Lakeshore Drive was lined with missile batteries. Yeah. These were 90 missiles. Each one of these has an atomic warhead and the nose. Here's the map of all the missile batteries around Chicago. This is the Lakeshore. Montrose, Burnham Park, Jackson Park, Grant Park, they were all missile batteries. You can see the Field Museum. The idea was the Russians were going to shoot this missile coming in over Lake Michigan, and we would madly shoot these things up at it. Our guidance wasn't great either. They would explode and you hoped you got it. Ground zero in Chicago was just about there. Kedzie and about 43rd. Yeah. Well, there are other things you can do with fission. You can make power plants. This is not the reactor, that's a cooling tower. The reactor is this little building right here. The way it works is pretty simple. You're going to set off your fission reaction. You have the control rods. You want more heat, you pull them up. Less heat, you push them down. The reaction happens. You circulate water once, circulate it again, and then circulate it again to cool it. The steam you make turns a turbine, and you make electricity. The weak links, if your control rods get damaged, you can't shut it off. And see these pumps? If the pumps go down, you can't cool it off. Hence, Fukushima. Earthquake, tsunami, melted down, big fire, lots and lots of radioactivity escaping. Today it looks like this. This is reactor number 1, and it's underwater. Now that's a good thing, actually. They let it flood, even though radioactive water's everywhere now. But they let it flood because water is very good at absorbing neutrons. It slows them down, and so that keeps this from continuing to react and overheating. In fact, let's pretend that this was working. After a few years, these little control things here, full of radioactive stuff, start to wear out. Not quite the kick they used to have. What do? Well, you put them in a giant swimming pool, of course. This is Morris, Illinois, 50 miles that way. Yep, you put them in water. Now you know the color. This is uranium-235 kicking out all its neutrons. The water is absorbing the neutrons. The glow is real. Turns out if you take a high energy neutron and run it through water, you get Turkinoff radiation, and it glows this bluish stuff. Yeah. Well, these are nuclear waste sites, swimming pools, just like a Morris. If you look at the map, well, we live in Illinois. We have lots of these sites here in Illinois. Somebody realized at ComEd that if you build these sites, people will send you their radioactive stuff because they don't want it around them. Used fuel in storage in metric tons. Who's number one in the country? We are. 9,000 metric tons of used rods all over the city. Well, people started to think that, gee, putting things in swimming pools might not be a good idea because they're still hot. If the pump system fails, they dry up, melt down, and you get huge radioactive clouds. The winds carry it right here. Don't want that. So the government said we'll come up with an alternate solution. Their solution. Turns out that they owned a mountain, again in Nevada, one they hadn't blown up yet. And somebody said, I have an idea. Let's dig a big tunnel down here, 1,000 feet down. And we're going to take everybody's nuclear waste, put it under this mountain. Yucca Mountain, it's called. So, they set up, dug these huge tunnels, trains going way underground to carry all this stuff, designed these massive trucks to carry radioactive waste. These are hot. Thermal imaging, they're hot. Nobody, however, had apparently taken geology. Why is there a mountain here? Mountain building occurs when tectonic plates push against each other, and then it breaks, and you get a mountain. So, this mountain exists because it's sitting on a break in the mantle below it. It's also referred to as an earthquake zone. They are planning on putting all this stuff right here next to an active earthquake zone. Not only that, this is 1,000 feet down. If you went down another 1,000 feet, where would you be? At the water table. 1,000 feet below the break here is the water table that serves Nevada. You get an earthquake, break open canisters, runs down the crack, and we're in trouble. Bad idea. Eventually, they said, this isn't going to work, is it? You know, maybe we can make it into a national park or something. Big tunnel going underground, lots of fun. So where is the radioactive waste? Still sitting in Morris. After it sits there for a number of years, it cools down enough that you can take it and very carefully encase it in solid concrete. There's space between them because they're hot. After this cools off, you can do something else with them. I don't know, scatter them in a pasture, whatever. I think it's for stage. So nuclear fission actually has a remarkable safety record, but the waste is a killer. Hence, fusion. Fusion power plants, just like we run on the sun. Hydrogen down to helium, lots of energy. We can't do that here, but we can take deuterium and tritium, fuse them together to make helium. None of this stuff is radioactive. You simply mop up the neutrons. Okay, that's good. So 20 years ago, we set about designing a device to do this. Been working on this 20-something years. It's huge. See the people? This is huge. It has never produced more energy than it takes to start it. The idea, though, you take your deuterium and tritium gas, put them in this big tunnel, surround it with magnets, then heat it up. Heat it up so much that it forms a plasma. The plasma is now charged. It's concentrated in the middle. Pressure builds, you get fusion. That's the idea. Doesn't quite work yet. If it did, you would simply have your fusion reactor here, pump water in, exchange the heat, turn the turbine. Simple as it can be, this could be coal-fired for all that matter. Except no waste. The big guy hasn't worked yet. This one is interesting. These are the lasers. They're all pointing in at one spot. They all fire at exactly the same instant. You put deuterium and tritium right there. This one worked about a month ago. They got more energy out than they put in. First time ever. That's a good thing. Problem is, you can fire these lasers twice maybe before you have to rebuild them. So it still needs a little bit of engineering. Something that's a hybrid that's very promising actually. This is about a yard across. This is built by Lockheed Martin at their top secret plant, this nicknamed the Skunk Works. So the Skunk Work thing is a combination of lasers, magnets, and whatever. This either has worked or soon will. And it's a yard across. MIT has one very similar. Again, haven't quite got it to work yet, but it will soon, I'm pretty sure. And this is the real major advance. The reason it's such an advance is that it's small. You can take this guy, a yard across, stick it in a plane, stick it in a boat, put it on the back of a trailer, anything, and you've got a power source. One of these guys on the back of a truck could generate 100 megawatts, 100 million watts of electricity. That's enough to do a small city. No radioactive waste. That's kind of amazing and very, very promising. So, number one, don't go home and make a bomb. I don't care if you have uranium laying around, it's a dangerous thing to do. Number two, fusion is probably the answer, and it's not that far away. Finally, we've added one tutorial, nuclear equations. Remember, you're shooting for 350 points. You do that, you get an A, and you don't have to take the final. Any questions? On Wednesday, we will meet in D204, and we will do chapter 12. Okay? All right, guys, have a good day, and good luck with everything.
Yeah. Yeah.
Honestly, talk to me. Yeah, you should.